All right, we're still talking about the effect and we're still talking about regression. What is regression again? Now remember, regression is a shape-fitting procedure. It's a line-fitting procedure. We pick a shape, and then what regression does is it picks the best version of that shape that could possibly fit our data, which sounds pretty good. We get the best version of a shape, but we still have to pick the shape. And sometimes if the shape is a bad shape to do, if it doesn't make sense for the data that we have, then we will get back a bad result. Even the best version of a bad thing still is a bad thing. And so if we're doing ordinary least squares sort of by default, sort of the most basic version of it, that shape that we are fitting is always going to be a straight line. However, some relationships are not going to be described well by a straight line. So here is an example. Here's a graph of some data, and you can see if you look at the data points, clearly there is not a straight line relationship going on there, right? The points are at a curve, and if we try to fit a straight line to them, as we're doing on the left there, it'll give us the best version of a line it can possibly do, but it's still going to be a pretty bad fit, because this relationship simply is not well described by a straight line. What if we could fit a nice curvy line like we have on the right here? Well, then that brings us to the topic of transformations. If we want to fit a non-straight line, if we have a relationship where the relationship between the variables is not represented by a straight line, sometimes we can fix this problem and still get a good fit with regression by simply transforming the variables such that maybe we don't have a straight line relationship with the original data, but maybe we do have a straight line relationship with the transformed data. And then that will solve our problem for us. Now, there are a number of transformations that are quite popular in statistical analysis. I cover a few of them in the book. There are more even that I do not cover, but we're going to focus on the two that you will most commonly see, especially in the world of causal inference and regression analysis. And those are polynomials and logarithms. So let's start with polynomials. Now, polynomials are a way of allowing a certain amount of curviness into your relationship. And what a polynomial is that you're simply adding additional powers of the variable to your model. So for example, this is a regression model that we've seen before, right? It's just a straight line. We could also call this, instead of a linear model, because there's a linear relationship between x and y, right? If you increase x by 1, y always goes up by the same amount, beta 1. That's a straight line, the slope never changes. You could also call this a first order polynomial, because what it includes is x to the power of 1 and nothing else. What if we add a second order term, right? This regression model includes a second order polynomial, also known as a quadratic. It includes both x and x squared. You don't want to leave the x out. You got to have both of them. Now this is a straight line component and a squared component. You can recognize this as sort of being like a parabola. Although if we zoom in far enough and only look at part of it, it's not going to curve back in on itself necessarily. So instead of having a straight line relationship, now we will allow a slight amount of curve to that relationship, which will allow us to fit a curvy relationship. We can keep going. We can add a third term to get a third order polynomial, or a cubic. This will allow us to get even curvier. Whereas parabolas allow for a curve, a cubic allows for a curve and then a curve back in the other direction. You can keep going. You could add a fourth order term for a quartic, fifth order term for a quintic, and so on and so forth. But I would say you're pretty much always going to be fine with the first three. After that, you don't want to get too wild with it for a couple of reasons. It makes your model kind of get weird if you have too many polynomial terms. So you don't want to just add them willy-nilly. But if you do have a curvy relationship, then yes, representing it with a polynomial is a good idea. Now, when we fit a line like this, right, what we are getting is not a straight line, but a line with some squares and cubes in it, which allows for some curves. And so we can fit a curved relationship. Just like we had on this graph here, this graph on the right uses a quadratic model. So it's got a second order polynomial, or it's got an x and an x squared in it, which, as you can see, allows it to fit that curvy data quite well. Now, in this case, we can see on the graph that the relationship is very much curvy and we need a polynomial. Another good way to think about this is by looking at the residuals of the model. If you look at the model on the left there, you can see that the residuals are definitely above the line consistently at the start. Then they dip below and then they come back above. That's not great, right? That suggests there's a relationship between the residuals and the x. We don't want that. Because remember, one of the assumptions that we need to make about the error term is that it is unrelated to x. But here, clearly, at low values of x, the residuals tend to be high. In the middle, they tend to be low, negative, and at the top end, they tend to be high again. We don't want that. This is a relationship between the residuals and x, and what we're really worried about is the relationship in the error term and x, but it's still not a good sign. So if you take the residuals of a model, and you plot them out, you should not see a relationship between the residuals and x. And if you do, that might be an indication that you might want to use a polynomial to get rid of that relationship. So here's a graph that just looks at the residuals for that same data, either fit with the model on the left with a straight line, or fit with a polynomial term on the right. And so we can see the residuals from this model. And you can see that on the left, there's a pattern left in the data, right? If you looked at this, you could say, oh, it looks like those residuals are changing along the x-axis, which you don't want, which might be an indication that you would want to add a polynomial term. And if you do that, in this case, if you add a quadratic, if you have a quadratic model, then you get the residuals on the right, which clearly has no relationship whatsoever. That's exactly what you want. So we have a model with polynomial terms in it. How can we interpret those polynomial terms? Well, things get a little bit dicey in the sense that you can no longer just look at one coefficient and know the effect of x. You can't do that anymore. Once x shows up in more than one place in your model, you need to consider all the places that it shows up in order to properly interpret the effect of x. And even weirder is that there is no single effect of x, and there shouldn't be, right? If you look at the relationship between x and y, what is the effect of 1 unit increase in x on y? Well, it's the slope of the line that we fit. And the slope in a model with polynomial terms is changing all the time. And so what our slope is, what the effect of x is going to be different at low values of x, small middle values of x, and high values of x. How can we find the value? Well, you take the derivative. You write out the equation. So here's an example with a cubic model. And you say, well, I want to know the effect of a 1 unit change in x on y. Well, what's a good way of describing change? You take the derivative. You take the derivative of y with respect to x. You write out that derivative. It's usually not that difficult of a derivative to take. This is like intro calculus stuff. And here what we have is the derivative of y with respect to x from a cubic model. What do we get in this particular case? We get beta 1, which was the coefficient on x, plus 2 times beta 2 times x, and beta 2 was the coefficient on x squared. And we also get 3 times beta 3 times x squared. Right? And you can see where this derivative comes from. If you just look at the original, you take the derivative, you get the second one. Now notice that x is in this equation, right? This is the effect of x. This entire expression is the effect of x. And so if I want to know what the effect of x is, I have to pick a specific x to have the effect at. If I plug in 0 for x here, I can say that the effect of x on y is just beta 1. All those other terms will drop out. And so what I can say is, at a value of x equals 0, the effect of x on y is whatever I estimate beta 1 to be. But for anything else, I need to calculate it directly. So if I say, well, what if I want to know the effect of x at x equals 1? If x is currently 1, what's the effect of increasing x further? Well, I would plug that in, and what I would get is beta 1 plus 2 times beta 2 plus 3 times beta 3. And I can plug in different values of x differently to see what I get. Here's a regression table from a model that has a quadratic term in it, and we can interpret the effect similarly. So this is the regression of the health inspection scores for a restaurant on the number of locations that particular chain happens to have. So we get a coefficient of negative 0.08 on the number of locations itself, and then we get a coefficient of 0.0001 on the number of locations squared. How can we get the effect of the number of locations? If you compare two different chain restaurants, one of which has one more location than the other, what's the effect on the inspection score? What's the association with the inspection score? Well, we would take the derivative. We would say, okay, the inspection score is equal to the negative 0.08 times the number of locations plus 0.001 times the number of locations squared. Take the derivative of that, I'll get negative 0.08 plus 2 times 0.001 times the number of locations. I can plug in any value that I want to get my effect. So if I'm looking at, say, 1,000 locations, what would I get? Well, the effect of a 1 unit increase going from 1,000 locations to 1,001 locations would be negative 0.08 plus 2 times 0.001 times 1,000. If I calculate that out, I get the effect of going from 1,000 locations to 1,001 locations on the inspection score. You can see how different this would be from if I picked a different x value. So if I'm looking at the number of locations at 0 or 1, let's say, what's the effect of going from 1 location to 2? Well, that would be negative 0.08 plus 0.0001 times 2 times 2, which is a much smaller number. So you can see the effect of x on y definitely varies across the range of the x-axis, as it should. That's what a curved relationship is trying to tell us, that the effect is going to be different at different values on the x-axis. All right, that is how we can work with polynomial terms, right? We can add a polynomial in order to allow the relationship between x and y to be nonlinear, to be curvy. We might do this in order to get rid of a pattern in our residuals, which we definitely don't want a pattern to be there. We don't want those residuals to be related to our x variable. Once we have our polynomial or terms in there, which maybe we have a quadratic, which is an x and x squared, maybe we have a cubic, which is an x squared, and x cubed, second or third order polynomial, we can then interpret that relationship by writing out the entire regression equation, taking the derivative, and then plugging in the values of x that we want to see what the effect of a 1 unit change in x is at those values. All right, that is it for polynomials. I mentioned logarithms. We're going to talk about those in the next video here.